Hello, my name is Peter Todd and my lab partner is Andrew Mickey. This is our video report for Lab 10 Semiconductor Light Sources in OPTI380A at the University of Arizona's Wyant College of Optical Sciences. In this lab, we studied the physical, optical, and electrical characteristics of the laser diodes and LEDs we've worked with in previous weeks. We measured and compared their structure, spectra, polarization, beam divergence, and their output power versus drive current with the goal of understanding how each type of source behaves. In Part A, we began by calibrating the microscope using a ruler to establish image scale. Then, we observed the LED and laser diode facets under low current to measure their emission areas and cavity length. From cavity length, we calculated the longitudinal mode spacing and compared it to the LD specifications, finding good agreement.
For Part B of the lab, we observed the spectra of LEDs and laser diodes. We started with the laser diode shown into the integrating sphere. We ran it at 20 milliamps, 22 milliamps, and 30 milliamps, which were below threshold, at threshold, and above threshold. We observed the emission spectra at each of these points, seeing more noise towards the bottom and a wider spectrum. We found a longitudinal mode spacing of 69.48 gigahertz. Moving on to the LED, we saw a distinct primary wavelength with a broader, wider spectrum than the LD.
In Part C, we began by measuring beam divergence by rotating each source and recording detected power versus angle. The LED showed a wide emission pattern while the laser diode produced a much narrower beam. Then, we used an adjustable polarizer to find the values where the recorded signal was highest and lowest to find the polarization ratio. We found a strong polarization ratio of about 16:1 for the laser compared to nearly unpolarized emission for the LED.
For Part D of the lab, we used the integrating sphere connected with the photodiode to find the power output of the LED and LD at different drive currents. For the LED, from the full range from 0 to 40 milliamps, as the current increased, the power output increased. However, we saw a different relationship with the laser diode, not seeing any power output until we had reached 20 milliamps. From then, it increased linearly all the way up to 40 milliamps.
From our measurements, the LED and laser diode showed clear differences across every property. The LED had an emission area of about 0.43 millimeters, while the laser diode cavity measured 1.18 millimeters, within about 1.7% of the 1.2 millimeter specification. Comparing our mode spacing values, Part A gave us 47.6 picometers, while Part B measured 69.5 picometers, a reasonable agreement given our experimental uncertainty. In the end, our data matched expectations for LED and LD behavior across emission size, divergence, polarization, and power characteristics. Overall, this lab gave us hands-on experience with semiconductor light sources and helped us see the differences between LEDs and laser diodes. And it was fun. Thank you for watching.